Before we start talking about how atoms bond, the first thing we need to do is just review a few concepts from our previous unit. So first of all, remember that valence electrons are in the outer shell of the atom, and you find it by using the periodic table. If you start counting on the left, you just start 1, 2, and then you skip over the D block, and you continue counting with 3 up until you get to the end of the columns, which is 8. So 8 is the most that you should ever get to. So the first thing is we need to draw Lewis dot diagrams, which are pretty simple. It's basically just the element symbol with dots representing the valence electrons on the outside. And I can't do it on this screencast, so if you're not sure about this, you can just see me in class if you missed today. But basically you have the element, and if you look at the periodic table, sulfur has 6 valence electrons. So if you picture it like a square, kind of like in this picture up here, it's a square, and you can fit 2 on each side for a total of 8. But sulfur only has 6. So for sulfur, you're just going to put 2 on one side, 2 on one side, 1 on this side, and 1 on this side. And it doesn't matter which 2 sides have the double ones, just as long as you have a total of 6 electrons on the outside. Barium is an alkaline earth metal, so it has 2 dots. And krypton is a noble gas, so it has all 8. So you'd have 2 on each side for krypton. Go ahead and pause this and see if you can find these elements and figure out how many dots you would put around each one. For nitrogen, you should have gotten 5, calcium is 2, cesium is 1, oxygen should have 6, aluminum is 3, and anytime you have less than 4, always spread them out first before you come back for seconds. So you should have 3, so 1 dot on each side. And neon has all 8. So just to review the octet rule, and again, this is just a review from last chapter, atoms are always going to try to achieve that stable octet, which is having 8 valence electrons. Whenever you have 8 electrons in the outer shell, it's going to be stable. Except for hydrogen and helium. So remember we talked about, since they only have an S, that first energy level, they only need 2 to become stable instead of 8, because they're so small. So let's review electron configurations briefly. Phosphorus, if you find it on the periodic table, you would put neon in brackets, and then you'd have 3s2, 3p3. And this is just review. We've done this for several weeks now. Magnesium, you would have neon in brackets, 3s2. And chlorine, you would have neon in brackets, 3s2, 3p5. So when we talk about becoming an ion, basically they're either going to gain or lose electrons to become stable. So phosphorus, if you look at what you wrote for the electron configuration, it's 3s2, 3p3. If it could just gain 3 more electrons to fit in that p orbital, it would have all 8. So phosphorus is always going to have a -3 charge. Magnesium is 3s2, so it could possibly gain 6 electrons and become -6, but that would be really difficult to do. It's easier just to get rid of those outside 2, because then the next shell is stable. So magnesium will always lose 2 electrons and become +2. And chlorine, same thing as phosphorus, it's going to fill up that p shell. So right now it's 3s2, 3p5. If you stick 1 more in that p so it becomes 3p6, then you've got a full octet and it's stable. So now we're going to talk about putting the atoms together. A chemical bond is an attraction between a nucleus of one atom and the outer electrons of a different atom. And there's 3 types of bonds. We're just going to talk about ionic for this video. The type of bond depends on how different the 2 atoms are in terms of their electronegativity. And that's actually really important. So once you write that down, I want you to circle or highlight or at least put a box around the words difference in electronegativity, those 3 words. Anytime I ask you, how do you know which bond it's going to be, it's based on the difference in electronegativity. And if I ever ask you the question, why do atoms bond, the answer to that question is to become more stable. So nature is always trying to reach the stability as much as it can be. So it's going to go towards stability. And the way the atoms bond is to reach the octet rule. So the answer to why is to become stable. The answer to how is to reach the stable octet. So let's talk about ionic bonding. This one is an attraction between positive and negative ions. So when you see the word ionic bond, just look for that little word ion in there and think about charged particles. And what happens is electrons are going to be transferred. Notice that's in red and underlined. That's an important word. For ionic bonding, you're transferring the electrons. And they're always going to go from a metal, because metals need to lose their electrons, to a nonmetal, because nonmetals need to gain their electrons. So it's a relationship between metals and nonmetals where the electrons are transferred. Once they're transferred, now the metals are positive and the nonmetals are negative, and so they're going to stick together. So here's a picture just to give you a visual. Notice that sodium has one valence electron, so if it gets rid of that one, this next shell here is completely full, so it makes it stable. Over here, chlorine has 7 on the outside ring, so it just needs to gain one more. So it would make sense for sodium to take this extra electron and give it to chlorine. When it does that, sodium now has a positive charge and chlorine has a negative charge, so they're going to stick together because opposite charges attract. Just another picture, you can see the electron transferring to the other atom. And here's an animation in case you like to see things actually move. So hopefully between the pictures, the words, and the animation, it'll help you remember it. So again, ionic compounds are formed from the transfer of electrons, and it always goes from the metal to the nonmetal. Since the metal is losing electrons, it's becoming positively charged. And remember, the fancy science word for that is cation. Look for that lowercase t, it looks like a plus sign. That's how you can remember it. The nonmetal is going to gain electrons, which makes it negatively charged, and we call that an anion. However, there's not always as simple as sodium and chlorine. So sodium and chlorine was just one electron that was involved, but sometimes it gets a little bit more complicated. For example, if you take calcium, which has these 2 valence electrons here, calcium needs to lose both of these in order to become stable. Well, if we bond it to chlorine, notice it has 7 outside electrons, so it only can gain one more, because you can't fit more than 8 into that outer shell. So if calcium and chlorine bond together, we can put this electron into this shell, but then we still have this leftover electron here. So then we'd have to have a second chlorine, so this electron is going to go towards that second chlorine. So the ratio for calcium to chlorine, whenever these bond, it's a 1:2 ratio, because it takes 2 chlorines to accept both of those electrons from calcium. For this page, I want you to actually draw the dots and arrows, but this is not something that I can just explain in words. I need to actually show you how to do this. So if you missed the class and you're just taking the notes, just skip over this page for now, and I'll show you how to do this once you get back to class. The next definition is for a chemical formula. And basically, it's just showing how many atoms you have in the smallest unit. So these little numbers down here, we call those subscripts. It tells you how many atoms you have. So for example, in this compound, you have 2 aluminums for every 3 sulfurs. And this is actually really important for formula units. It's the lowest whole number ratio of ions. The lowest whole number ratio of ions. And the key word there, the word I want you to highlight or circle, is the word ratio. So ionic compounds don't actually form little tiny compounds called molecules. Molecules are only for covalent. For ionic, all we're talking about is a ratio of ions. So if you take into consideration sodium chloride, where you have 1 sodium and 1 chlorine, that doesn't mean that you only have 1 sodium and 1 chlorine that are floating around together as partners. What it means is, in a big crystal of sodium chloride, you would have 1 sodium atom for every 1 chlorine atom. So it's a 1-to-1 ratio, but it doesn't mean that you only have 2 atoms. 2 atoms would just be a molecule, and we'll talk about that in our next lesson. So for ionic compounds, there's not really a set unit. It's not like 1 sodium and 1 chlorine. What it ends up looking like is this crystal here. So notice that you have 1 purple for every 1 orange, and since it's a 1-to-1 ratio, we write it NaCl. But it doesn't mean that we just have 1 Na and 1 Cl. What it means is that the ratio between them is a 1-to-1 ratio. So again, the key word there I'm trying to stress is ratio. And a crystal, in case you're not familiar with that word, it just means you have a repeating pattern. So for example, NaCl is a 1-to-1 ratio. MgCl2 means that every time magnesium bonds to chlorine, it's always a 1-to-2 ratio. You have 1 magnesium for every 2 chlorines. It doesn't mean you only have 3 atoms. What it means is in that big crystal, it's a 1-to-2 ratio. Same thing here. This is a 2-to-3 ratio. It doesn't mean you just have 5 atoms. It just means that the ratio between the atoms is a 2-to-3 ratio. And since it's a ratio, you do need to simplify. So once you get your formulas, if you ended up with something like 3 and 6, notice that they're both divisible by 3, so you need to simplify that to 1 and 2. Keep in mind that all ionic compounds are electrically neutral, and what I mean by that is that the positives are going to balance out the negatives perfectly. So if you have a +2 charge for your positive, you have to have -2 for your negative. So the sum of the charges will always equal 0. Sometimes we call that the net charge. If you ever see that on a test or quiz, if I say what is the net charge of an ionic compound, I'm talking about what is the sum of that, which would just be 0. And there's a shortcut way to do this that doesn't involve the arrows and dots, and I'll try to explain it over the video, but if you don't understand it, just come see me at lunch and I'll show you how to do this on paper. Basically, all you have to do is put the charges first. So sodium has a +1 charge, it has 1 valence electron, so you're going to put +1 right here in the top right corner. Sulfur is -2, so you're going to put a -2 right here. Then you're going to take each number and crisscross it down to the opposite element. So sodium has a +1, you're going to crisscross that down to the sulfur. Lost my mouse, there it is. So here's the +1 up here, bring that 1 down to sulfur as a subscript, and for sulfur take that 2 and bring it down to sodium. And once you stick them together, you no longer have to show their charges. They're still there, you just don't have to show them anymore. So it becomes Na2S, that's your formula. Let's try to do one more. For this one over here, magnesium is a +2, so you would put a +2 right up here. Bromine is a -1, so you're going to put a -1 here. When you cross those down, the 1 comes down to magnesium and the 2 comes down to bromine. So your final one, whoops, let me go back. Your final formula should be MgBr2. So what that says is for every 1 magnesium, you need 2 bromines to match up with it. And the reason is because you have to make the charges equal 0. So if magnesium is +2, bromine is -1, then those don't add up to 0. But if you have 2 bromines, now you've got -1 and -1, which is -2. That balances out the +2 for magnesium and makes the whole thing equal to 0. Let's look at another one. Strontium is +2. Oxygen is -2. So when you bring those 2's down, it ends up being SR2O2, but that can be simplified, so you're going to just make it SRO. +2 and -2 already balance out to 0, so it's just a 1-to-1 ratio. And same thing here, gallium is +3, nitrogen is -3, so if you crisscross the charges down, you get Ga3N3, which can be simplified to just GAN. And here's some more examples you can try on your own and let me check it when you come back to school. But again, if you're not sure what you're doing here, just skip it for now and I can easily show you this on paper. And the last thing are just some properties of ionic compounds. So they tend to be solid crystals, and what's in red is what you really need to memorize. They have high melting points, which means that it takes a lot of energy to break it apart. They are hard and brittle. And they can conduct electricity, but make sure you note that it's only under certain conditions. So they have to have their electrons free to move around in order to conduct electricity, and in the solid state, the electrons can't move around. So in order to conduct electricity, you have to have it into a liquid form, and there's 2 ways you can do that. You can either literally melt it into a liquid, so if you took some sodium chloride and held it over a flame, it would melt into liquid sodium chloride. Or you could just take the sodium chloride and dissolve it into water, and that allows the electrons to move around as well. So again, it can conduct electricity, but only if it's melted or dissolved in water. And that's all for ionic compounds. Next time we're going to do covalent for the next video.